So in this video, we're going to start our learning unit 6, which focuses on discrete random variables. And before we dive into it, let's recall some definitions that we covered in earlier chapters, namely what is a random variable and what is a discrete versus continuous random variable. So let's take a look. Here's a definition. Random variable is a variable typically represented by x that has a single numerical value determined by chance for each outcome of a procedure. Now, notation for the random variable, we will use capital letters towards the end of the alphabet, such as Q, R, S, T, U, V, W, and etc., to represent random variables. Okay, here's in order to make a probability statement about random variable, one must create an event first. So for example, if X is the number of siblings of a randomly selected student, then when X equals 2 is an event in which the number of siblings of a randomly selected person is 2. Now, to denote the probability of that event, we put capital letter P, and then in parentheses, we're going to write X equals 2. So the event when number of siblings equals 2, and P is the probability of that event. All right. Now, random variables, discrete and continuous random variables. Some examples of random variables. The product of the dice when 2 fair dice rolled. The number of 6s when 4 fair dice are rolled. The number of cars in the randomly selected family. The household income of a randomly selected household. The lifetime of a randomly selected bulb. And there are many other examples. These are just some examples of random variables. Now, let's recall the discrete versus continuous random variables. So for the discrete values or random variables, we have distinct separate values. There usually can be listed even though it may be an infinite list of numbers, but they could still be listed. And I'll give you some examples and explain a little bit more of what that means. And then for continuous random variable, it could be any value in an interval, and it's impossible to list all the values. So let's take a look at some examples. It says identify random variables below as discrete or continuous. So result of flipping a coin once. Okay, if we flip a coin once, what can we get? What kind of values can our random variable take on? So we know we could get either heads or tails, and we could assign 1 to our random variable if we get heads, and 0 if we get tails. So the values of our random variables are 0 or 1. Clearly, we can list all of the values, and this is a discrete random variable. Now, the next one is exact mass of a random animal selected at the San Diego Zoo. Let me switch to the paper, because I want to spend a little more time on this question. So let's say we have the smallest animal versus the largest animal. So we're going to have some kind of an interval. So for the smallest animal, I mean, depending on how you define an animal, but we could say that bacteria is an animal too. So the weight of that animal is close to 0. And let's say the heaviest animal in the San Diego Zoo is an elephant. And I don't know how much elephant weighs, but let's say it's, for the purpose of this exercise, is 5,000 kilograms. So any other animal in the zoo is going to be in this interval between 0 and 5,000. So that is a finite interval. However, the number of values in this interval is infinite, right? So for example, let's say a horse, and let's say a horse is 225 kilograms, right? But then if we have a very accurate measurement, it could weigh 125.79 kilograms, or if we actually make it even more accurate, it could be 225.79065 kilograms, so forth. We could actually continue on improving our accuracy, and there is actually infinitely many values there, right, that we can come up with depending on how accurate our scale is. So basically, and same for any other animal in the San Diego Zoo, there is an infinite number of possible values. It's impossible to list all of those values. So therefore, we're going to conclude that this variable is continuous variable. It's not a discrete variable. The next variable that we will discuss is variable y, which represents the year that a randomly selected student was born. Okay, so we're talking about a population of students, and let's see. Let's say, so we could have a number of years, between, how about 1922, that student would be 100 years old, but hey, if they want to come to college, they're welcome. And probably the last year would be 2012. So the person would be 10 years old, but again, if they're brilliant, they could still go to college, right? So we would have a list of numbers between 1922 and 2012. Would the list be long? Yes, but can we still list all the numbers? Yes. So we conclude that this variable y is a discrete variable. Okay, the next variable is variable z, which represents exact number of ants born tomorrow in the universe. Well, we don't know how many ants are out there, so we could only speculate. But let's say it's, I don't know, quadrillion 271. We have a lot of ants born. Now, the question is this discrete or continuous data? Can we list the number, like theoretically? Not that anybody would want to do that, but theoretically, if we really wanted to do that, had all the time on our hands, could we do it? And I'd say probably yes. Our variable z, the exact number of ants born tomorrow in the universe, is going to be our discrete data value, because it's a countable number. It's a very large countable number, but it is a countable number, and it's a discrete data value. However, for such large values, we're gonna, for practical reasons, they're easier to handle if we're gonna treat them as continuous variables. And large data like that, a quadrillion something, we're going to handle it as continuous, but about that a little later. Let's talk about variable W. The winning time for the 100-meter dash in 2016 Olympics rounded to 2 decimals. And I want you to pause here and try to answer this question. And the answer is variable W here is a discrete value because it says we can have values such that 9.58, 9.59, 10.00, 10.01, so forth. So we can list a number of values and they're rounded to 2 decimal places. Now, what happens when we change the description of our variable? Now, variable W is the exact winning time for a 100-meter dash in 2016 Olympics. Well, the exact time is not the time necessarily the time that you see on the clock, right? So so we could on the clock, for example, we could see 9.58, but in reality it could be 9.579 or 9.5792134. So there is an infinite number of values between 9.58 and 9.59 that we are actually missing. So if we're not rounding to 2 decimals like in the previous example, and we're talking about the exact winning time, then it could be anything, right? In a certain interval, let's say between 5 seconds and 12 seconds, for example. Because maybe larger than 12 seconds would not be a winning time anymore. And yeah, so, and 5 seconds is the least humanly possible. I don't know, maybe they'll beat it one day, but it could be any, it's a finite interval, but the values, there's infinitely many values inside of this interval. So based on that, our variable, the second variable W, let's call it W2, is actually a continuous variable. Okay, so this chapter in this unit, we're going to focus on discrete variables. And next, we're going to talk about probability distributions of discrete variables.